Hey guys, today I'm going to discuss multiprocessor scheduling, which is the basic topic of my discussion. This is my report that I have created. This is a multiprocessor scheduling in operating system. Here you can see something table of contents, background detail, overview, implementation. Let me move down to something which is of more relevant. Here I am using MFA. These are the already two techniques that are available in the market. One is called as MOGA, another one is called as NSGA2. Now what the basic difference is, the MFA produces better results than case of MOGA and NSGA2. I have just modified this MFA and just analyze the result how this modification can make this MFA better. This is my overall use case architecture which can be used to explain. This is the user, this is the task graph. I have provided the two ways. This is the task graph that is user is going to pass as an input. These are my three major functions that I'm going to do. One is called as my mean field handling, compute the fitness and allocation. These are some of the activity diagrams, class diagrams which help you to understand what I have done. The user can interact in two ways, either through the text file or through the GUI. Once the user provides the input, it computed the fitness values. From these computed fitness values, you are going to compute the spins. After computing the spins, you produce a new schedule. Now this new schedule computes its own fitnesses. Then we decide whether this solution is of great importance to us. If it is of great importance, we add it to the dominated solution. If not, we discard it and again compute the spins. This is reach the maximum. We are going to set how many dominated solutions we want. So this is the maximum and this is the stopping condition. So let us start with what we have done. So let me start with my base research paper. My base research paper basically says that we are going to compare the we are going to have the three Pareto fronts. One is called as my make span time, other one is called as my average flow time, and the third one is nothing but called as my reliability, right? This is the algorithm how I calculate this make span time and reliability. This is the algorithm through which I decide which task is to be passed to which of the processor, and what I obtain in the result is something like this. This basically tells me about a particular schedule. You are allocating this task to a different processor. You can clearly say that from first figure and second figure you can have a difference that task 1 is allocated to first processor, task 1 is allocated to second processor, and some other differences in the allocation of the task, but the task rate schedule remains the same: T0, T4, then T1, then T6, T5, T2, T3, T7 and T8. This is basically done to ensure that there is no dependency problem, right? What you get that making the task first and allocating it to different processor, we are going to get a different results of the objective function. In the first case, we are going to get an objective function of 220, then 210. That means I'm just optimizing. Lesser the value of objective function, better will be the result. These are the three non-dominated set that I get after applying. These are my three non-dominated set. This is for MOGA, this is for MFA. The same thing holds for MFA as well, that you are just making a difference in allocation to the processor, and what you get in the objective function, one you are getting a value of 200, then you are optimizing the objective function 8. So what's the importance in this? So you are just getting an approximate dominated solutions, non-dominated solution set. Now let us see what we have done, how we have implemented it. So here is I have implemented is NetBeans 8.0 and I have used JDK 8.1, JDK 1.8, sorry. These are my few of the major classes: chromosomes.java, chromosome2d.java, fitnessfunction.java, graph.java, implementer.java. So what you basically have to do, you just have to run this implementer.java. Now let us say what is my input and what I get as an output. This is my input. This is my basically my graph function that I'm passing it as an input. This is the inter-process communication cost. This is 40, 100, 10, 10 and so on. This is my execution time. These N1, N2, N3, N4, N5 basically denotes my task number, and this is basically a dependency graph. This has been passed as an input. Let me run again. So I'm running again. My class name is implementer.java. So these are my output. Let me see them. First of all, look at this screen. This screen tells me about the final allocation to the processor. The task 1 is allocated to this processor 0. The task 2 is allocated to the processor 1. Since initially both of the processors are empty, so the start time is 0. End time is 20, which is basically nothing but equals to my execution time of that task. Fine, so this is basically the final allocation of the processor. Now this is of great importance. These are the Pareto friends which I am going to technically talking about. Fine. So what we can say, we are going to get a value of 300, 100, 210, 290, 100, 210. So you can compare this value from this value which has been provided in the research paper. The research paper values is 200, 116 and 215, 180, 106 and 225. So you can say the value you have obtained is not optimized for first part, that is a mix span time. However, it has been optimized for both the part, because I am getting a value of 106 and 210, which is the value which has been provided in the research paper, right? And this is again my final processor allocation, which basically says the T1 is allocated to the processor 0, 1 and so on, which basically has been depicted in the two ways. One is on the CMD and other is on the screen. Now this is my processor task schedule computed by my friend Rajat and Uday. This is basically the name of the person who are doing the work on this project. One is me, that is Rajat. This is my processor 0, processor 1, processor 2, and these are the tasks that I have allocated. If you browse in this, you will get nothing but the execution time of the task. And moreover, now let me discuss about this my presentation that I have created for better understanding of what I have done. These are my current problem that I try to accommodate optimization of multiprocessor scheduling algorithm, huge scope in dynamic scheduling, multi-objective scheduling algorithm to prove useful single objective. Basically, this I am talking about heterogeneous distributed computing system. In the heterogeneous distributed computing system, multiprocessor scheduling with multi-objective is of great importance as compared to multiprocessor scheduling with a single objective. These are the three witness functions: F1, F2, F3, make span time, average flow time, reliability, and which I am called as Pareto fronts. This is my task graph that I am passing as an input. This is my energy function, which is of great importance, right? The first energy function basically try to accommodate, minimize my connection cost. However, the second objective function basically look about the precedence. Here I am using a constant lambda. There is the lambda value I am taking is 0.7. I am using, as you know, this is a genetic operation, so I am using an order crossover for this. This is my parent 1 and parent 2, and these are the possible children that we generate. These are the few steps of the genetic algorithm used. These are basically my three major classes: implementer.java, meaningful annealing.java, fitness.java. Now let me show you one more thing, which I call as creativity. See here I am having a class named GUI.java. If I run this class, this is a new way that I think the user should use to provide an input. Instead of providing the input in a text file like this, say you are having this my project. So here input of providing the input like this, that is a input in the format of number of processor, task, execution time, cost. That is basically the task graph I have shown. The better way to provide an input is through GUI. Let me see how I provide the input. Let us say I take three processors. Fine. So these are my three processors. Now what I can do, I can provide the task dependency graph. Now I provide this. Say I put control and click T1 processor, then click T2 processor. It says T1 is added as the parent of T2. Again, if I click T1 processor, T3 processor, it will say T1 is added as the parent of T3, T2, then T4, T2, then T5, T2, then T6, T6, then T7, and T7, then T8. So I just got a dependency graph. Now I say compute my allocation. So this is what I get. This is my final processor allocation based on my dependency graph. The execution time and the start time it has taken is on random basis. These are my tasks that has been allocated to processor 0, processor 1 and processor 2. This is just a new way to provide an input, nothing else. This is my allocation. Thank you friends, thank you for listening me and understanding my project. If you have any problem then you can mail me on my mail ID which is rajatbothrajain@gmail.com. This is my mail ID. You can mail me on this for any reference. Now I'll show what I have put all together. This is my major project report, which will consist of my use case diagrams, class diagrams, which will help you to understand the results better. So let me come to the point. So this is my activity diagram, which basically says how it is working. This is my class flow diagram, and this is my use case diagram. Next we are going to have a base paper. This is the base paper which I have used. It is a base paper of 2013 IEEE conference paper solving multi-objective multiprocessor scheduling using mean field annealing. These are the some of the important reference paper we should must read to understand what this paper basically have to say. What we have done, we have just basically modified this function and obtained that the last two Pareto friends result has been optimized. These are the two Pareto friends, this 160 and 215. These two are optimized. However, it does not get so much good result for the objective function 1. These are all the reference papers that I have used. Here, this is the reference paper for the crossover that I am discussing all about. So this is basically tell me an OX operator. It basically stands for order crossover. And the great paper that I have referred is this multiprocessor scheduling using mean field annealing. This is the function that I have used, but some modification has been made. This is the research paper of say around 1990s, right? And the recent research paper is of 213. So why I'm showing this research paper is this, see this energy function. This is the energy function of this research paper, right? This is of 1990 something. And see this research paper, which is my base research paper. This is my energy function, right? And see this research paper. You can clearly say that this summation part here and this summation part here is approximately equal. But in addition to this, I have added these two objective as well. So you can say this is of single objective and this is of multi-objective, right? That's all I have to say. My base paper, my report, and my presentation is here. My project is here. This is a major project SEM7, which consists of my SRC file, major project 7 core file. These are the codes that I have created. This is the GUI for creating the GUI that I have just shown to you. That's all. At last I have to say one thing. Let me say on notepad. Thank you for listening. Hope I don't bore you. Have fun, great guys. Bye. Let me close. Don't see my desktop.